One beautiful way to solve this Laplace inverse question is to use the convolution theorem of Laplace transform. So you can solve this one using partial fractions. You can break this one down using partial fractions, and then you apply the linearity property of the Laplace inverse. But here I'm going to solve this one using the convolution theorem. So if you can recall the definition of the convolution, so if we have f of t, right, this is convoluted with g of t. This is not multiplication. That is f of t convoluted with g of t. This is defined as the integral from 0 to t of f of t minus tau. This is multiplied by g of tau and then d tau. Right. So this is the convolution of f of t and g of t. Right, so now we found the Laplace transform of this convolution. So the Laplace transform of the convolution of f of t and then g of t, we got this one to be f of s, which is the Laplace transform of this function multiplied by, this is normal multiplication, multiplied by the Laplace transform of g of t, which is capital G of s. So we established this result in my previous video. So if we take the Laplace inverse of the right hand side, so the Laplace inverse of f of s multiplied by g of s, this one is going to return the convolution, right? So this one is going to be f of t convoluted with g of t, like this. So here it's just like taking the Laplace inverse of the product of two functions in terms of s. So if you are given this to solve and you are asked to use the convolution theorem, you have to break this one down into the product of two functions, just like what we have here, f of s and then g of s. So let's go ahead and break this one down into the product of two different functions. Cool, so now let's do that. So this one is the Laplace inverse. Our original function can be written as 1 all over s to the third. This is one function multiplied by 1 all over s squared plus 1. If we multiply these two functions, we are going to get our original function, right? And now this one is going to be what? So the Laplace inverse of f of s multiplied by g of s is going to be f of t convoluted with g of t, right? So f of t is the Laplace inverse of this one, right? So this one is going to be the Laplace inverse of the first one, and the first one is 1 over s to the third. And this is convoluted with the Laplace inverse. This one is the Laplace inverse of this guy. So this one is convoluted with the Laplace inverse of 1 over s squared plus 1, like this. Cool. So now what is the Laplace inverse of this? So I can rewrite this one as this, and just using this one so that we can split it into the product of two different functions. So this one is 1 over s to the third, and this is multiplied by s squared plus 1, like this. And this is equal to, what is the Laplace inverse of this one? So for the, if we can recall, we are recalling now. So if we have the Laplace transform of t squared, if we can remember this one is going to be 2 factorial, which is 2 divided by s to the power 2 plus 1, which is 3. Right, so that means that if we are taking the Laplace inverse of 2 over s to the third, this is going to return our function in the t world as t squared. So this one looks like this, right? But what we are missing is the 2 on top. We do not have 2 on top. So I'm going to remove the 2, I'm going to remove the 1 on top. After doing that, I'm going to replace the 1 with 2, and then I'm going to take it away by dividing by 2, like this. So I now have the Laplace inverse of 2 over s to the third, and that is t squared. So this one is going to be 1/2 times t squared, like this, and this is convoluted with the Laplace inverse of 1 over s squared plus 1. So if we are familiar with our Laplace tables, this one is just going to be the sine of t, like this. So what we are asked to find, the Laplace inverse of our function 1 over s to the third multiplied by s squared plus 1 is just 1/2 t squared convoluted with sine of t. But we can't leave our answer in terms of a convolution like this. We will have to find what this is. What is 1/2 t squared convoluted with sine of t? We are going to use the definition of the convolution, which is what I wrote here. So that means if we are able to find the convolution of 1/2 t squared and then sine of t, that should automatically be the Laplace inverse of this function here. So good luck with the convolution. So the convolution, we are now going to have this 1/2 t squared convoluted with sine of t. What is that? That is an integral, right? So it's going to be the integral from 0 to t. Right, if we can go back to the definition of the convolution, multiplied by f of t minus tau. What is t in this case? F in this case. So our function f here is like t squared. So this 1/2 is a constant. I'm going to bring it out in front here. Why not? And then f is the t squared, and then g is the sine of t. So I have f of t minus tau. So that means in place of t, I'm going to replace that with t minus tau. So this is going to be t minus tau by a squared. So this is f of t minus tau, right? And this one is multiplied by g of tau. G in this case is sine of t. So that's going to be sine of tau like this. And then d tau. That is, you are integrating with respect to tau. That's what we have here. So this Laplace inverse problem is now converted into an integral problem. So now let's tackle this integral. I'm not going to write this one all along, and that will be a waste of time. So now let's have this 1/2 in front here, and now we have the integral, right? We have the integral from 0 to t. Now let's FOIL this. This one is going to be t squared minus 2t tau, and then plus tau squared, and this is multiplied by sine of tau and then d tau, right? So this is equal to 1/2 in front, and now we can distribute in with the sine of tau. That is going to be t squared sine of tau minus 2t tau, and then sine of tau, and then plus tau squared, and then sine of tau. All this one is integrated with respect to tau. I'm going to go ahead and split this one into two different integrals. Three different integrals. So the first one is going to be 1/2. So we are integrating with respect to tau, right? So the t's are constant. So this t, I'm going to pull it out of the first integral, and I'm going to have the integral from 0 to t of sine of tau and then d tau. This is the first integral. The second one is going to be minus 1/2, right? So minus 1/2. And then this 2t is a constant. It comes in front as well, so it's going to be 2t like this. And then the integral from 0 to t of this one is tau multiplied by sine of tau and then d tau, right? And then the last one is going to be plus 1/2, and then there's no constant here, so this is 1/2. The integral from 0 to t of tau squared and then sine of tau and then d tau like this. So this 2 and this 1/2 and 2, they'll cancel. So what I'm going to do, I'm just going to clean these ones because they're going to cancel out, leaving only t, right? So that is what we have here. So let me see what it is. Okay, so I'm going to clean this one. So 1/2 and 2 will just cancel, leaving only t, right? So this is what we have. All right, cool. So now permit me to now call these ones, let's say I1, integral I1, integral I2, and then integral I3, and tackle them one after the other. So I1 is equal to 1/2 t squared, and then the integral from 0 to t of sine of tau and then d tau. This one is equal to what? So 1/2 t squared, and then integrating, sine of tau is going to be what? Negative cosine of tau, right? And then the limits of integration from 0 to t, and this is equal to what? So now we plug in the limits of integration. So that is going to be negative. I'm going to pull that one out because it's difficult to be handling negatives. And then plug in t. This is now going to turn to cosine of t minus plug in 0. That is going to be minus cosine of 0. Right. So I1 here is evaluating to negative 1/2 t squared. And then inside is going to be cosine of t minus 1. Because cosine of 0 is 1. And this one is going to reverse to 1/2 t squared into 1 minus cosine of t. This is what we have. Or we can just distribute in the 1/2 t squared. That is going to be 1/2 t squared minus 1/2 t squared and then cosine of t, like this. This one is the first one, first integral. Now let's go to the second one. Why not? Let me switch colors. So the second one, I'm going to do it in green. Why not? So I2 is equal to t, then the integral from 0 to t of tau and then sine of tau, and then the tau, like this. Alright, so this one we are going to use integration by parts. So what I normally do, di method. So d for differentiation and I for integration. I'm going to differentiate tau, right? So this one is plus, next one is minus, and I'm going to integrate sine of tau. So differentiating tau is 1, differentiating 1 is 0. Integrating sine of tau is negative cosine of tau. Integrating negative cosine of tau is going to be negative sine of tau. So just the product, so the integral is just the product of diagonal terms, nothing special. Alright, so this I2 is equal to the product of diagonal terms. So the first one is going to be negative. So there's already t outside, so which is what I have here. And then product of diagonal terms, negative tau times cosine of tau. Right, and now negative, that's going to be positive, right? So plus sine of tau, like this. And then the limits of integration from 0 to t. So next one here is going to be 0 times the next one here, which is 0 anyway, so there's no need integrating for the third time. Cool stuff. So I2 is equal to what? So now t, and now let's plug in the limits of integration. So we just replace tau with t. So this is going to be negative t cosine of t and then plus sine of t. This is the upper limit minus the lower limit. We plug in 0. 0 times cosine of 0 is 0, and then sine of 0 is 0. So the lower limit is 0. There's no need to write it. And then I2 is going to evaluate to this. Let's distribute in with the t. So this is going to be t sine of t minus t squared and then cosine of t, like this. So this one is I2. Job done for I2. So now let's go to I3. Let me do that in white. Why not? So I3 is 1/2 the integral from 0 to t. I3 is equal to t. I'm sorry, there's no t. So I3 is going to be 1/2 the integral from 0 to t of tau squared and then sine of tau and then d tau. This is I3. That is what we have here as I3. So now this one is integration by parts again, but this one is a little bit longer because it has t squared. Okay, cool. So now let's differentiate and integrate. So I am going to differentiate tau squared and then integrate sine of tau. This one is plus, so this one is going to be 2 tau. When you differentiate 2 tau again, you're going to get 2, and 2 you're going to get 0. So this is the plus negative. Integrating sine of tau, that's going to be negative cosine of tau. Integrating negative cosine of tau is going to be negative sine of tau. And integrating negative sine of tau is going to be positive cosine of tau. And now we are done. So we just have to multiply diagonal terms. This one, and then this one. Next one would have been 0 times whatever integral, the value of the integral will be here, but 0 times any value of the integral is going to be 0. So there's no need. So I3 is just a product of the diagonal terms. So this one is going to be 1/2 all the way in front. Now the first diagonal term is going to be negative tau squared and then cosine of tau. Right, the next one is going to be negative, that's going to be positive. So plus, this is going to be 2 tau and then sine of tau. Right, and then last one is going to be positive again, that's going to be plus 2 cosine of tau, like this. This one we are done with the integration. Put the limits of integration from 0 to t. So now let's plug in the limits. So the upper limit is very easy. You just replace tau with t. So 1/2 all the way in front, negative t squared cosine of t plus 2t sine of t plus 2 cosine of t We are done with the upper limit. What about the lower limit? Lower limit for tau, this is going to be 0. This is going to be 0, right? And now the only thing that will not be 0 is this one, because cosine of 0 is 1. So it's going to be minus 0 plus 0 plus 2 times the cosine of 0. So this one is going to be minus 2 times the cosine of 0, because cosine of 0 is not 0. And it's minus because we are subtracting the lower limit from the upper limit. Now let's distribute y naught with the half. So it's going to be negative 1/2 t squared cosine of t. Half and 2, that's going to be plus t times the sine of t. And then this one is going to be plus cosine of t. Right, so the half and the 2 will cancel, and then minus 1, because this one cosine of 0 is 1, so 2 times 1 is 2, and then 2 times 1/2 is 1. So this is the value of the integral I free. Now we just have to go back and then put everything together. So 1/2 t squared convoluted with sine of t. Okay, so 1/2 t squared convoluted with sine of t. So 1/2 t squared convoluted with sine of t. This one is equal to a combination of 3 different integrals. So the first one is I1, and I1 is 1/2 t squared minus 1/2 t squared cosine of t. This one is going to be 1/2 t squared minus 1/2 t squared cosine of t. This is I1. And our next one is going to be what? Next one is going to be minus I2, right? So minus this I2, and this is I2. So minus, and this is I2. I2 is t sine of t, and then minus t squared cosine of t, minus t squared cosine of t. This is what we have. I think this thing is a malfunctioning for now. And now the last one is going to be plus I free, right? So plus I free. So now let's write the I free, and this is I free, and this is going to be minus 1/2 t squared minus 1/2 t squared cosine of t plus t times sine of t plus cosine of t minus 1, right? So this is what we have. So 1/2 t squared convoluted with sine of t. This is equal to 1/2 t squared minus 1/2 t squared cosine of t. Now this one is going to be minus t times sine of t plus t squared cosine of t, right? I'm just distributing with this guy, and then minus 1/2 t squared cosine of t plus t times sine of t plus cosine of t minus 1. Will there be any cancellations? Let's see. So this one 1/2 t squared cosine of t, 1/2 t squared cosine of t, they are going to combine to t squared cosine of t, which is going to cancel with this t squared cosine of t. So these 3 terms will cancel. Next one is going to be negative t times sine of t, which is going to cancel this positive t sine of t. And what is left is the answer. So I'm sorry, this one should be in yellow pen for consistency. So 1/2 t squared convoluted with sine of t, this is equal to 1/2 t squared. So 1/2 t squared. And then what is left? What is left is plus cosine of t. Plus cosine of t, and then minus 1. I think my system is malfunctioning right now. So this one is the convolution of 1/2 t squared and sine of t. And then the convolution is the Laplace inverse of what we are asked to find. So this one, the Laplace inverse of 1 over s to the third multiplied by s squared plus 1 is the convolution of 1/2 t squared and then sine of t. So we have found the convolution of this, and that is equal to the Laplace inverse of our function. Therefore, the Laplace inverse of what we are asked to find is the convolution of what we found here. So the Laplace inverse, we are now wrapping up. The Laplace inverse of 1 over s to the third multiplied by s squared plus 1 this one is equal to the convolution of 1/2 t squared and then sine of t, which is 1/2 t squared plus cosine of t and then minus 1, like this. And this one is the answer to our Laplace inverse problem. So I will leave this one to you as a homework. So we can try to find a Laplace transform of this. If you find a Laplace transform of this one, we are going to arrive at this answer, which is 1 over s to the third multiplied by s squared plus 1. So this is by using the convolution theorem. So you can, as I said earlier on, you can work this one by using the partial fraction decomposition. You break this one down into several fractions. You find the constants, and then you take the Laplace inverse, applying the linearity property of the Laplace inverse, and you are going to arrive at this same answer. And the Laplace transform of this answer is what we have. So that confirms our answer is right. So this is the convolution theorem. If you find this one helpful, please give me a thumbs up and subscribe to Calculus Diaries for more tutorials on Laplace transforms.